Hello everyone. Today we will explore machine architectures through the lens of Flynn's taxonomy. This classification system provides a simple, structured way to categorize computer architectures based on how they handle instructions and data streams. Understanding the classification is essential for analyzing performance and designing efficient computing systems. To make these concepts clearer, we will illustrate them with practical examples and real-world applications in computing. Finally, we will introduce some widely used programming models in parallel computing that fit particularly well to some computer classes within Flynn's taxonomy. By the end of this discussion, you'll have a better understanding of how different computational models work and why they matter in today's technology-driven world. To set the stage, let's first consider how computers process information. At the most basic level, a computer can be thought of as a single processor executing instructions on data stored in memory. Now, over time, improvements in hardware design have introduced new techniques to increase computational efficiency. Some of these key advancements include the following. 1. Vector processing, where we have specialized hardware which executes the same operation on multiple pieces of data simultaneously. There's also multiple processors, which allow multiple independent processing units or cores to work in parallel. And finally, there's also caching mechanisms, which improve performance by storing frequently used data closer to the processor for faster access. Now, in the case of vector and multiple processing, the performance enhancements stem from different key principles of how data is processed concurrently or in parallel. However, concurrent data processing needs to be facilitated by the underlying hardware the program is being executed on. More precisely, the architecture of the hardware must permit parallelism. This is where Flynn's taxonomy comes into play. Flynn identified 4 fundamental types of architectures. It categorizes computer architectures based on 2 fundamental dimensions. 1, how many instruction streams the system can execute at once, and 2, how many data streams the system can process simultaneously. This classification results in 4 distinct categories of computer architectures, which we will examine in detail. Understanding these classifications is essential as they form the foundation for modern parallel computing and help us analyze performance characteristics at a high level. Let's begin our exploration of machine architecture with the simplest model: single instruction, single data, or SISD. This is the most fundamental form of computation where a single processing unit executes one instruction at a time on one piece of data. It is the foundation of traditional sequential computing. In a SISD system, the processor fetches an instruction from memory, retrieves the necessary data, executes the operation, and stores the result. This process is then repeated for the next instruction. This is how a von Neumann computer functions. Now let's consider a simple computational task, adding 2 vectors A and B element by element. If you were doing this with pen and paper, you'd begin by reading the first element of A and the first element of B. You'd then add them together in your hand, and finally, you'd write the result into the first element of your result C. Then, you'd move on to the second element, and so on. Similarly, in an SISD system, the processor first loads the first value from vector A into the register. Second, loads the corresponding value from vector B. Third, performs the addition. Fourth, stores the result in vector C, and then repeats the process n times for vectors of length n. Now, each step happens in sequence, meaning that the time required grows proportionally with n. The runtime from this process will be 2 times the load, plus the addition, plus the store, all of that multiplied by n, the number of elements in your vector. Now, usually, load, add, and store require multiple clock cycles depending both on hardware and context, such as data placement. The key characteristic of this architecture is that everything happens sequentially. There is no parallelism involved at the hardware level, and that the time required scales 1-to-1 with the number of operations to be performed. While this may be acceptable for small-scale problems, it quickly becomes insufficient for large datasets. Now, as computational workloads increased, a natural question arose. What if we could process multiple pieces of data at the same time using the same instruction? This idea led to the single instruction multiple data, or SIMD, architecture. SIMD enables a single instruction to operate on multiple data elements simultaneously. Instead of processing one number at a time, as in SISD, SIMD divides the workload across multiple data points in parallel. This is achieved through specialized hardware such as vector registers, which can hold multiple values at once. To use a real-world analogy, imagine you're chopping carrots for dinner. The single instruction single data model corresponds to a workflow of 1. Placing the carrot on your cutting board, 2. Cutting it into slices, and 3. Putting the carrot slices into a bowl to make room on your cutting board for the next carrot you want to chop. In SIMD, we would instead 1. Align several carrots on the cutting board, 2. Slice the carrots simultaneously with each cut, and 3. Remove all the carrot slices from the cutting board to make room for the next batch. This reduces the number of operations, in this case cutting motions, required, making the process significantly faster. Now, to revisit our vector addition example, a SIMD-enabled processor would first load 2 values, A1 and A2, from vector A into a register that can hold both values. Then it would load the corresponding 2 values, B1 and B2, from vector B. It would perform a vector addition in each of these registers simultaneously, and finally store the 2 values in vector C at positions C1 and C2. Then it would repeat the process n½ times to cover all elements 2 at a time. The runtime for this process will then be 4 times a load operation plus an add operation and 2 store operations multiplied by n½. Here we accomplish the same task as in the SISD case while issuing half as many addition instructions. In tasks which are dominated by the computation time, this can yield a significant speedup at the cost of loading multiple pieces of data from adjacent locations in memory simultaneously. Modern processors incorporate SIMD instructions to accelerate tasks such as graphics processing, machine learning, and scientific simulations. Most modern CPUs possess dedicated hardware to support vector operations with SIMD instruction sets, like AVX and SSE. GPUs are heavily based on SIMD principles and take it to the extreme, executing the same operation across thousands of data points in parallel. However, SIMD has its limitations. It is only effective when the same operation needs to be applied to multiple independent pieces of data. If a computation involves dependencies between data or between operations, other forms of parallelism may be more suitable, which brings us to the next architectural category. MISD. MISD stands for Multiple Instruction Single Data. Now, pure multiple instruction single data architectures, where we have multiple processing units working on the same data, are generally uncommon. They're used, for example, in systems which need to be fault tolerant. If one processing unit, for example, encounters an error, its results can be knowingly dismissed because the same computation has been performed redundantly by other processors. However, most modern processors nevertheless take advantage of so-called pipelining, which is very much akin to MISD. To elaborate on this concept, let's take a step back and examine what happens when a computer executes a single operation. At a high level, when we write a simple line of code, such as C equals A plus B, it may appear as if the computer performs just one operation. However, under the hood, multiple steps are required to complete even this seemingly simple task. A processor typically follows these stages. Instruction fetch and decode. The CPU retrieves the instruction, C equals A plus B, from memory, and it interprets the instruction and determines what needs to be done. Load data. The processor loads the values of A and B from memory or registers. Compute. the arithmetic logic unit, or ALU, performs the addition, and stored data, the result is written back to memory or a register. Now, each step in the instruction process takes place in different physical parts of the hardware. Memory load units fetch the data, while instruction decoders are responsible for decoding instructions. Inside the chip, built-in control logic continuously runs to manage disk processes. Memory controllers handle the data load and tell the memory load units what to do, transferring information between memory and the processor. The actual computation happens in a dedicated part of the chip that processes arithmetic and logical operations. Finally, once the computation is complete, the results are stored in different sections of the machine, such as registers of memory, ready for future use. As you can see, each of these tasks occurs in different areas on the processors, often represented as distinct units within the chip. By staging their use, we can increase the throughput of the processor. Now, imagine a scenario where while one part of the chip is busy performing a computation, another part is idle. Wouldn't it be more efficient if the processor could start working on the next instruction while still finishing the previous one? This leads us to the concept of pipelining, a fundamental technique used in modern processors. A pipeline allows different stages of multiple instructions to overlap, much like an assembly line in a factory. Consider, for example, an assembly line in a factory where workers specialize in different tasks. One assembles parts, another paints, another inspects the final product. Instead of waiting for each product to be fully assembled before starting a new one, multiple products are worked on at different stages simultaneously. One product can be inspected, a second one painted, while a third one is currently being assembled by a different worker. Now here's how it works. The CPU fetches an instruction, decodes it, and then issues the load. However, while it does the load, it can immediately start fetching the next instruction. During this process, we are still using a single data stream, but we are now applying multiple instructions. This corresponds to the multiple instruction single data, or MISD model. By overlapping different stages, we achieve higher instruction throughput, making it seem as though the processor is completing multiple instructions per time interval. Almost all modern processors incorporate some form of pipelining. However, pipeline efficiency depends on factors such as pipeline depth, the numbers of stages in the pipeline. Now, deeper pipelines allow for a greater overlap of concurrent operations, but can be vulnerable to stalls. Which brings us to hazards and stalls, where in situations where an instruction depends on the result of a previous one, the dependency can cause delays. Advanced processors use techniques like out-of-order execution and the branch prediction to mitigate these issues. We'll discuss these in a moment. Pipelining is one of the key optimizations that allow MISD architectures to perform better than their basic sequential counterparts. It significantly improves efficiency and instruction throughput, bridging the gap between simple sequential execution and more advanced parallel computing models. Now, we mentioned out-of-order execution before. Out-of-order execution is another critical optimization in modern processors. Unlike traditional sequential execution, where instructions are processed in the exact order they appear in the program, out-of-order execution allows the processor, not the compiler, to analyze the instruction stream and reorder operations for better efficiency. For example, consider a simple operation like C equals A plus B, where C, A, and B are vectors, followed by I++, where I is just a loop counter. In a purely sequential system, the second instruction would have to wait until the first is fully completed. However, modern processors can recognize that these operations are independent and executed simultaneously as long as there are available resources. This technique greatly enhances performance, especially in workloads where dependencies between instructions are minimal. However, it requires significant hardware support, including additional transistors and complex scheduling mechanisms. As a result, some processor generations have experimented with disabling or limiting out-of-order execution to balance cost and performance. Another pipeline optimization technique was speculative execution. Speculative execution allows a processor to preemptively execute instructions before determining whether they are necessary. One key example is branching. In traditional execution, encountering an if statement disrupts the pipeline as the processor cannot determine the next instruction until the if condition is evaluated. However, with speculative execution, the processor guesses the likely outcome, decodes and fetches the next instruction in advance, and only commits the result if the prediction is correct. While this approach improves efficiency, it introduces branch misprediction risks. If the processor follows the wrong execution path, it must discard the incorrect computations, leading to wasted energy, performance penalties, and famously produce hardware insecurities. High branch misprediction rates can severely impact efficiency, particularly in complex code with frequent conditional statements. Finally, let's finish understanding the last model in Flynn's taxonomy: multiple instructions and multiple data, or MIMD. MIMD allows different cores to execute completely different instructions on different data. This flexibility makes MIMD well suited for complex computations that require varied operations across multiple processing units. In modern computing, parallelism occurs along multiple axes. For instance, each core or processing unit has its own instruction stream. Each unit also operates on its own separate data at any given time. In large-scale systems, different nodes in a distributed environment also function independently. This independence among processing elements defines MIMD, which forms the vast majority of modern computing hardware, from your phone to the largest clusters in the world. To better understand MIMD, consider a simple loop that processes a vector of size n. A common approach in parallel computing is to split the iteration range among multiple processors. Suppose we have two processors at our disposal. The processor 1 runs the first half of the iterations and processor 2 runs the second half of the iterations. If the workload is uniform for all iterations, then you might expect the overall runtime to be halved. This kind of workload distribution is fundamental in parallel computing frameworks such as OpenMP and MPI, where loop iterations can be divided among available hardware. Each processor executes its own set of instructions independently. A single program runs on distinct processors, but each works on a different subset of data. There is no synchronization between processors unless explicitly required. And even if processors operate on data stored in a shared memory pool, their computation remains separate unless communication is needed. Most modern processors do not conform to a single category from the models we have just studied. Instead, they combine multiple paradigms of SIMD, MISD, and MIMD. Pipelining, MISD, is present in nearly all processors to improve instruction throughput. Vectorization, SIMD, is common in CPUs and GPUs to enhance performance in tasks like image processing and scientific computing. Multithreading and multi-core architectures, MIMD, are standard in virtually all computing devices today. Having discussed all four categories of Flynn's taxonomy, we should venture into a brief excursus on hyperthreading now. Building on the role of pipelining in optimizing instruction throughput, modern processors employ additional techniques to enhance performance further. One such technique is hyperthreading, a form of simultaneous multithreading, or SMT, that aims to maximize the utilization of computational resources. You can think of a thread as a programmed sequence of instructions. Simultaneous multithreading describes the capability of a processor to execute multiple threads simultaneously by providing 2 threads per core. In the hyperthreading approach, parts of the chip are duplicated to support 2 threads, frequently those parts responsible for fetching and decoding instructions. However, expensive portions of the chip are not duplicated. For example, the floating point units responsible for the bulk of scientific computation, which limits the relevance for computational tasks. So while 2 threads can run in parallel most of the time, whenever they need to execute floating point operations, they must synchronize and take turns. This creates a bottleneck. You can see where this might work well for tasks that rely mostly on integer calculations, where the floating point units aren't needed as often. In those cases, it almost feels like having two distinct processors because all other pipeline resources exist redundantly. A useful analogy would be a car production line. Imagine that the chassis is built in parallel, the tires are mounted in parallel, and the car moves smoothly to the assembly stages. However, when it comes to installing the engine, a crucial expensive component, only one car can proceed at a time. If many vehicles in the pipeline don't require an engine, then the process remains efficient. But the moment every car needs an engine, the entire system slows down at that bottleneck. When hyperthreading is enabled, we often see twice the number of threads reported when we monitor system performance, but they don't necessarily contribute to twice the computational power. The CPU simply pretends to have twice as many processing units. While this does improve concurrency in some cases, it doesn't mean we double the real performance. Thus, this technology is mostly useful for computational use, which emphasizes responsiveness to a user who is requesting many distinct small pieces of computation with relatively short runtimes. For example, how a person uses a typical computer instead of a cluster. For these reasons, it's ubiquitous in x86 consumer hardware, but it remains a poor solution for high-performance screenshotting. Finally, now that we have explored the different machine architectures in Flynn's taxonomy, let's turn our attention to how we program these machines. Many of our programming models still inherit a great deal from the SISD description. There are fundamentally two categories of parallel programs depending on how instructions and data are distributed across processing units: symmetric and asymmetric. In asymmetric programming, we have separate code for each node or core that is in use. In some architectures, each processing unit or node executes its own distinct piece of code. A common example is a client-server architecture, where one node may act as a database server while another handles the client requests. This approach requires careful coordination between different units to ensure proper communication and synchronization. However, client-server architectures are relatively rare in high-performance computing because the necessary coordination and data transfer process is not well suited to the performance characteristics of clusters. In many high-performance computing or HPC applications, we take a different approach. Instead of writing separate code for each node, we use the same program across all processing elements. This programming model is known as Single Program, Multiple Data, SPMD. Although the acronym SPMD contains 4 letters, it is important to note that this is not part of Flynn's taxonomy. Instead, SPMD is a programming paradigm, not a classification of hardware. The key idea behind SPMD is that each individual chip runs the same instruction stream, but they all have their own data to work on. SPMD is commonly used on MIMD, multiple instruction, multiple data architectures, as SPMD allows each processor to execute the same program at its own pace and on its own data. This means that different processors might be working on different tasks at any given moment, depending on the data they are handling. For example, imagine you're simulating weather patterns across a country. With SPMD, each processor runs the same weather simulation program. One processor might be analyzing cloud movement over the mountains, while another is tracking ocean temperatures. They don't need to stay in perfect sync. Each one works through the simulation independently. This flexibility makes SPMD one of the most widely used approaches in high-performance computing, where large-scale problems are divided across many processors to solve them efficiently. To wrap up, we have now a better understanding of how Flynn's taxonomy provides a powerful framework for understanding different computing architectures. Each of these models plays a crucial role in modern computing. Beyond these classifications, SPMD, Single Program, Multiple Data, has become a dominant programming model, particularly so in high-performance computing, allowing multiple processors to work on different parts of a problem simultaneously. Understanding these architectures is essential for anyone working in computing, as they form the backbone of both hardware design and parallel programming. As technology continues to evolve, leveraging these principles effectively will be key to optimizing performance and solving increasingly complex computational challenges. Thank you very much for watching, and see you in another lecture.